Hello friends, welcome back for another deep learning project, cards classification. Here we will classify the playing cards with the compact convolutional transformer. So first we will discuss about the architecture and its advantages and disadvantages. Then we will implement, train and do the inference. So let's move to the notepad to discuss about the compact convolution transformer. Let me increase the font. Okay, compact convolutional transformer. The compact convolutional transformer is a vision model that combines convolutional layers and transformer based attention to process image efficiently. The compact, let me make it CCT, the compact convolutional transformer is a vision model that combines convolutional layers and transformer based attention to process images efficiently. It is designed to improve data efficiency, that means with fewer number of examples or dataset we can train the model and get a high accuracy. So what is that? It is designed to improve data efficiency, that means lower data also it can perform well, and computational cost while maintaining high performance. Unlike pure vision transformer, compact convolutional transformer introduces convolutional token embedding and removes class token dependency, making it more compact and better suited for small datasets. So let's discuss on architecture of the compact convolutional transformer. We will have a convolutional token embedding layer. Instead of directly splitting an image into pitches like what vision transformer does, we will use convolutional layers to generate image tokens. These convolutional layers extract spatial information before feeding data into the transformers, reducing the number of tokens needed. This helps in learning local features before applying global self-attention. So what does this layer? Instead of splitting an image into pages, which is done by vision transformer, compact convolutional transformer uses convolution layers to generate image tokens, which avoids class token dependency. These convolution layers in the token embedding layer extract spatial information before feeding data into the transformer, reducing the number of tokens needed. So it reduces number of tokens needed. As the number of tokens decreased, that's why automatically computational cost also decreases. I hope you are understanding this. Then, as the convolution layers are used here, that's why the model learns the local features before applying global self-attention, that is the transformer layer. So what it does, helps in learning local features before feeding applying global self-attention, that is transformers. Then after this layer we will have a transformer block, that is a transformer encoder. It's not a single layer. The conv token embedding is not a single layer. It is, I think, it's 2 or 3 layers. Let's discuss while we implement that. Okay. Now, in transformer encoder, similar to vision transformer, compact convolutional transformer has a stack of transformer encoder layers with multi-head self-attention and feed-forward networks. However, it does not use a class token. Instead, it applies a pooling layer to aggregate final features, and it uses attention pooling or sequence pooling. So let me write to understand better. Similar to vision transformer, compact convolution transformer has a stack of transformer layers with multi-head self-attention and feed-forward networks. I repeat, the transformer encoder in compact convolution transformer has a stack of transformer encoder layers with multi-head self-attention and feed-forward network. So when we discuss the theory, you won't be getting full information about it. When we apply or implement it, you will understand better. So don't worry about that. We will implement line by line each code. So in the transformer encoder, while the vision transformer uses a class token, but here we will be using a pooling layer, that is a sequence or attention pooling layer to aggregate final features. So it uses an attention pooling layer or a sequence pooling layer to aggregate final features instead of a class token, just like vision transformers. Okay. And also the compact convolution transformer uses stochastic depth for regularization. So stochastic depth, which randomly drops a set of layers. During inference, the layers are kept as they are, and it is much similar to dropout, but only that it operates on a block of layers rather than individual nodes present inside a layer. So stochastic depth is used for regularization, which randomly drops a set of layers. During inference, the layers are kept as they are. It is much similar to dropout, but only that it operates on a block of layers rather than individual nodes, which is touched by dropout layers present inside a layer. In compact convolution transformer, stochastic depth is used just before the residual blocks of transformer encoder. In compact convolutional transformer, stochastic depth is used just before the residual blocks of transformer encoder. So this is nothing but the architecture of the compact convolutional transformer. First, it will split images into patches and generate image tokens, then apply transformer with multi-head self-attention to that. That's what compact convolutional transformer. It's very easy. So let's discuss advantages and disadvantages. As I already told that these are better at data efficiency. That means small data sets also works well with this. Better data efficiency. You can see it reduces number of tokens needed because of convolution. convolutional embeddings, which leads to lower memory requirement. Yes or no? Because of number of tokens reduced, we don't need a high memory or a large memory. That means memory requirement is smaller, and which improves the training or which speeds up the training because of low memory requirement. So let me write this as convolutional embedding reduces the number of tokens, leads to lower memory requirement and faster training. And the next advantage is that as we are using convolutional layers for splitting an image into patches, that's why it does a stronger local feature extraction. What it does a stronger local feature extraction. Then also I told that we don't need any class tokens, so which is also a advantage. No need of class token. And these are some of the advantages of compact convolutional transformers, and let's discuss the disadvantages of compact convolutional transformer. While the compact convolution transformer is more efficient than vision transformer, still it uses self attention. Yes or no? Here you can see we have multi-head self attention layers, so which can computationally expensive than standard CNNs. What is the disadvantage? As it uses self attention, which is computationally expensive than standard convolutional neural networks. As it uses self attention, which is computationally expensive than standard CNNs, but these are more efficient than vision transformers. So when we compare with CNNs, it is a disadvantage, since the compact convolutional transformer relies on convolution for embedding. Yes or no? We are using convolutional token embedding. It may not leverage the power of pure self attention compared to models like vision transformers. As we are using convolutional layers for embedding, that means it will not fully leverage the power of pure self attention, just like vision transformers. That's also a disadvantage. So let me write that since CCT relies on convolution for embedding, it may not fully leverage the power of pure self-attention compared to models like vision transformers. These are some advantages and disadvantages of compact convolutional transformers, and let's move to the Kaggle notebook to implement what we have discussed now, and let's do the cards classification. So we are here in Kaggle notebook. Let's implement the compact convolutional transformer. Before implementing, make sure that you have the accelerator GPU T4 if you want to accelerate your training, and also make sure to have this cards image dataset as your input, and okay. So first of all, I have imported the required libraries like TensorFlow, Keras, Matplotlib, NumPy. TensorFlow and Keras are for implementing the layers and the model. Matplotlib is for data visualization. NumPy is for numerical calculations. Let me run this. Okay. After that, using the mirror strategy method in the distribute module of TensorFlow, I am creating the strategy for using the GPU runtimes, which are my accelerators for training my model, and seeing the number of replicas in the strategy, which will return 2 because we have 2 cores in the GPU T4. So let me run this. You can see it has returned 2. That means we have 2 cores in our strategy or in our GPU accelerator. After that, I am generating 2 datasets, a train DS and a validation DS, using the dataset cards image dataset classification. From there, I am using the train subfolder and copied this path, and that is above here. Using that directory for generating the datasets, and I have a subset equal to both argument in the image dataset from directory method, which will return these 2 datasets, that is train DS and val DS. Then I have the argument validation split equal to 0.2, that will split the whole dataset into 2 parts, where 80% are reserved for train DS and 20% are reserved for validation DS. Then I have another argument seed equal to 1337. This argument will regenerate the same dataset when we compile our notebook. Then we have the argument shuffle equal to true to shuffle the datasets. Then we have levels equals to inferred, that means the levels will be inferred from the datasets, and we are resizing the images of the datasets into height of 128 pixel and width of 128 pixels, and then we have 64 examples in each batch of the datasets. Let me run this and create the two datasets, trained DS and well DS. So you can see we have total 7624 image files belonging to 53 classes. As we know, we have 53 playing cards in a deck of cards, so we are having 53. I think it is 52, but one is added in these classes, that's okay. And from 7624 image files, 6100 files are reserved for training and remaining for validation. And to get the class names of all these playing cards, we have the attribute class names, which is applied to the trained DS, and the class names are stored in the class names variable. And from the class names I am printing the first 5 class names. Let us see that by running this cell. So you can see 5 class names are ace of clubs, ace of diamonds, ace of hearts, ace of spades, and 8 of clubs. These are first 5 class names. After that, I am taking one batch of trained DS and showing the cards, 9 cards with their class names, and let's see the cards and the class names. For that, I am iterating over the batch, then over 9 iterations, then selecting a subplot and using ANSO method of pyplot to plot the image, and removing all the axes available in the image, then showing a title. Let's run this. So you can see this is an image of king of cards. This is a card of 2 of diamonds, and this is 6 of spades. This is queen of clubs, this is queen of diamonds, 3 of hearts, 8 of hearts, 10 of diamonds, 10 of diamonds. After that, I am augmenting the train DS and validation DS. So in augmentation, we have a rescaling layer which will scale down all the values of the image pixels into the range of 0 to 1. Then we have a random flip layer which will flip horizontally to each layer. Using a method and iterating over the layers, we are just doing the image augmentation, then returning both image and level after the augmentation. So to apply that augmentation to the data sets, we are using the map method, where we have provided the augmenter function and another argument number of parallel calls equal to tf.data.autotune. This argument allows tensors or TensorFlow to decide how many parallel threads to use when applying the map function, which improves the CPU utilization. Then we have added prefetch equal to tf.data.autotune. This will preload the next batch in the background while the model is training, which reduces the data loading bottlenecks. Similarly to train DS, we are also applying the same to validation DS. Let's run this. So we have successfully done the augmentation. So let's build the compact convolutional transformer. So at first we have a tokenizer which will tokenize and generate tokens. So in tokenizer, in the init method, we are passing output channels as a list of two integers. One is 64 and another is 128. Output channels are nothing but the filters of convolutional layers, and here we are having a sequential model where we will add two convolution layers, that is of 64 number of filters and 128 number of filters, and in each convolution layer we have 3 cross 3 kernels, and we are doing the ReLU activation after convolution operation. Then we are removing the bias and using the kernel initializer as he normal, which will initialize the weights of the convolution layer. Then after the convolution layer, in each block we will have a zero padding layer. Zero padding layer adds zeros to the kernel in the input. Then we are adding a max pooling layer with 3 as kernel size and 2 as strides, and we have the padding equal to same. Then as we have discussed that the CCT tokenizer will do the tokenization, that's what we will implement in call method of CCT tokenizer layer. So first thing of that is using this conv model or sequential model, we are passing images to that and getting the outputs, and that outputs are saved in the outputs variable. From that we are finding out the height, width and channels of images, and we know a batch has 4 elements tuple, where the first one is the batch size, the next one is height, and the next one is width, and the final one is number of channels. That's why we are taking out the second one from the outputs SAP and naming that H for height, then third one for width, that is W, and the final one, that is number of channels. Then we are doing nothing but just reshaping the outputs so that we can use that for encoding in the transformer. So sequences generated from the image are reshaped to the shape of this. -1 is used when we don't know the actual size to convert, and h into w will result into the number of patches that the outputs have, and c is number of channels. So sequences of this shape will be produced when we reshape the outputs, and the sequences will be returned. And the build method is used for building the layers weight, while get config and from config are used for serializing and deserializing Keras objects. Here in our case we have serialized output channels and deserialized the same output channels. So let's run this tokenizer layer. Okay, it's done. After that, as I told, we will be using a sequence pooling layer. So in sequence pooling layer we will just do some operations like softmax, transpose and matrix multiplication. After that we will squeeze out the output. So here the inputs are passed through a dense layer, and the outputs of the dense layer is softmaxed. After softmaxing we will do the transpose, or we will find out the transpose of the softmaxed values to these axes, and then we will do matrix multiplication of inputs with the softmaxed and transposed value. Then we will squeeze the output we get after matrix multiplication. So that is what is sequence pooling, and I also repeated the same build get config and from config to build the layers weight and serialize and deserialize the Keras objects. So this is what we do. I am repeating the sequence pooling again. First of all, we will be using a dense layer, and we will pass inputs to the dense layer, and outputs of the dense layer will be softmaxed and then transposed to this axis 0 to 1. After that we will do matrix multiplication of transposed output with the input which is received to the sequence pooling layer, that is x in our case, and finally we will squeeze out the output we get after matrix multiplication. That's what sequence pooling or sequence pool is done. Let's run this. After that, as I also told that we will be using stochastic depth for regularization. So in stochastic depth we will get drop probability, which will drop a set of layers, then a random seed generation to get regenerations, then if it is training or the model is training, then only we have to implement the stochastic depth. While it is doing inference, it should not be implemented. That's why we have training argument in the call method, and if training, then we will subtract the drop probability from 1 because the probability ranges from 0 to 1. So we will get, when we drop the number of layers, then we will get how many to keep. That's what the probability says. After that we will do this operation. The main purpose of this is to drop some layers and keep some layers. So we have a random tensor which is generated using uniform distribution and added to the keep probability value. Then we have multiplied the input with random tensor and divided with the probability and returning that, so that some layers will be used and some will be dropped while training. And if it is not training, we will simply pass the X. Then we have two methods, get config and from config, to serialize and deserialize Keras objects. Let's run this. After that we have the feed forward network, that is multi-layer perceptron. Here we are passing input X, number of hidden units, and dropout let. So iterating over the hidden units list, and here we will have a dense layer and a dropout layer, where dense layer will have GALU activation function and dropout layer will have some dropout rate. So usually in hidden units it is of a list of two values or two integers. Let's run this feed forward network or multi-layer perceptron. So you can see the stochastic depth rate is 0.1, that means 10% will be dropped in each iteration. We have only two transformer layers. Let's run this. Now the main thing comes, we will build the compact convolutional transformer model. So first we will get a input of image size 128 with 3 channels. Then we will tokenize the image using CCT tokenizer, or we will get the patches when we use the CCT tokenizer. After that we are generating stochastic depth probabilities. That's nothing but a continuous value spaced uniformly. Then we are implementing a transformer block. In every transformer block we will be iterating over some range of transformer blocks, that is number of transformer layers, and inside the block we will have first a normalization layer, then a multi-head self-attention layer, then we will have a residual connection, again a layer normalization and a feed forward network, and a residual connection. But as we discussed that in CCT, stochastic depth is used just before residual blocks in the transformer encoder. That's why we have added the stochastic depth just before the residual part here and also here. So one thing I want to say that whenever you use same key and value pairs, then the multi-head attention turns to multi-head self-attention. As we are providing x1 and x1 as key and value to the multi-head attention, that's why it is becoming self-attention. So in this CCT we have a layer normalization which is regularly used in transformer block, then a multi-head attention layer which is also regularly used or generally used in transformer block, then a stochastic depth just before the residual connection, then again a normalization layer, then a multi-layer perceptron or feed-forward network which is also generally used, then again a stochastic depth just before residual connection which is in general. After doing the self-attention, we will do the again layer normalization to normalize the values returned by the transformer blocks or the final transformer block. Then we will pull out the features from the output we get after normalizing using the sequence pulling layer, and finally we will use a dense layer for classifying the inputs into their respective classes. So in the dense layer I have passed number of classes as the number of units and softmax as activation function, then building the Keras model using the model and passing inputs and logics as its outputs and returning the model. So let's run this. After that I'm building and compiling the model under the strategy.scope, that is the scope of the GPU accelerator. So make sure that you have the optimizer loss and matrix defined under the scope whenever you compile under the strategy or GPU accelerator. Let's compile the model. After that we will train and evaluate our model. So using the fit method we are training the model, passing the train ds and 50 epochs and val ds for validation and checkpoints as callbacks. And checkpoints are nothing but the model checkpoints which will be saved when each epoch completes in the file cct.keras, and our model checkpoint monitors validation accuracy and saves the best when the maximum accuracy is reached in each epoch. So let's run and train our model. So it will take some time. Don't be worried about the time, I will speed it up. after the 50 epochs, we have achieved a training accuracy of 0.8869, that means 88% accuracy, and loss of 0.3484 as training loss, and validation accuracy of 0.6562, that is 65% accurate, and we have achieved highest validation accuracy equals to 0.6627, that is the highest validation accuracy, and in validation loss we have reached 1.5049. so somewhat model is overfitting, it's okay. After that, let's evaluate our model with respect to validation data set. So let's run this. So after evaluating, we are getting the accuracy of 0.66 and loss of 1.61. So let's fetch the best model from the checkpoints we have saved in the load in the file location cct.keras using the load model method, and evaluate that best model with respect to validation dataset. So it is resulting the best model is of 0.65, that is 65% accuracy. So we will be using this model instead of this best model because it has higher accuracy. But one thing you should notice that the loss here is high, then the loss in the best model is low. Therefore utilizing the best model is a good pick for our inference. After that we will do the inference. So first of all, we will take out some images from validation dataset and iterate over the first 9 images, and the original images are these. Then expand the dimension of the image so that we will add the batch axis to the original image. Then using the best model, we are predicting the image and saving that in the prediction variable. After that we will find out the index of the prediction, and that level will be shown using the title. And as we have saved class names in the variable class names and passing the index through the level variable, we will get the class and show that as title, and we will show the image using the IMShow to the original image. After that we will remove the excesses present over the plot and show the image. Let's run this. So you can see all 9 images are successfully executed. So see the model predictions. This is 3 of hearts, yes, our model is predicting correctly. This is 9 of hearts, yes, the model is predicting correctly. This is 6 of hearts, but it is 4 of hearts, the model is predicting incorrectly. And 10 of diamonds, this is also incorrect. 6 of hearts, this is also incorrect. Queen of hearts, this is correct. King of hearts, correct. 3 of clubs, correct. King of spades, correct. Let's rerun this and check the next batch. It is showing same. Let me change the batch to 2. So see 8 of clubs correct, 6 of clubs incorrect. This is 9 I think, or 6. This is jack of diamonds correct, 9 of diamonds, correct. 9 of clubs, correct. King of hearts, correct. Ace of spades, correct. Queen of hearts, correct. 10 of spades, correct. So around 66% accuracy our model is resulting. So let's save the best model in the file path model.keras. Yes, we have saved. So to use the saved models, go to the output section, and here you can see cct.keras, that is checkpoints of our training, and this is the model.keras, which will contain the model configuration and compile information. So you can download both using the three dots and clicking over the download button, and use that for in your practical applications. So I'm not going to do the second part of this video, that is building the user interface for this project, because I got some serialization and deserialization error. If you found any mistakes, please do not hesitate to put a comment in the comment section. Thank you for watching me patiently. Thank you very much.